So let's look at the scalar product of vectors, also known as the dot product of vectors, and also known as the inner product of vectors. So let's say we have two vectors in some n-dimensional space. N could be two-dimensional space, it could be three-dimensional space, it could be n-dimensional space. So vector u has components u1, u2, all the way up to un, depending on the dimension of the space, and v has components v1, v2, all the way up to vn. All right. Then the dot product, or the scalar product, or the inner product of these two vectors is each of the components u dot v is pronounced u dot v is u1 times v1 plus u2 times v2, and in a similar way the sum of each of the like components multiplied together and just summed. Technically, this scalar or dot product is the, technically speaking, is the product, is a map from the product of Rn with itself into the reals. Okay, whatever your dimension n is, it's a map from the product of Rn with itself into the reals. That's the technical definition. Okay, so let's have a look at an example here. So our first one would be, let the vector u have components 2, 5, -3, and v has components 5, 2, -1. All right, so the scalar product of these two then is the first component of vector u multiplied by the first component of vector v, so 2 times -5, plus then the second components of both vectors multiplied together, plus the third components of both vectors multiplied together. When we do that, we get -10 plus 10 plus 3, which gives us 3. So the scalar product is 3. Okay, as you can see, a mapping then from R3, from the product of R3 with itself, to R. Okay, let's go down now, have a look at the angle between two vectors, and we'll bring back the cosine rule to look at this, but we have two vectors, vector u and vector v. There is an angle between them. Okay, and the vector u minus v, okay, it's the vector u plus the negative of vector v added on, okay, to give you the sum of this. Okay, so that's a vector pointing from here to here in this direction. Okay, so from previous videos there, just imagine this vector here, take its negative, so flip it 180 degrees and translate it over and attach it to the end of u, because it's u plus the negative of v. So you can imagine a vector pointing down here, like that. We're free to translate vectors about on the page. The origin can be anywhere. Okay, and then the net is this. Alright, so it's the same as this. Okay, cosine rule tells us that the magnitude of u minus v, that's a new vector, this vector here, the magnitude of this vector here, u minus v squared, is the magnitude of u squared plus the magnitude of v squared minus 2 times the magnitude of u times the magnitude of v times the cosine of the angle between them. Okay, now we also know, as we will, I will cover a little bit more of this in future vectors, but in future videos, but the magnitude of u minus v squared is the same as u minus v dotted with itself. Okay, so u minus v dotted with u minus v gives us the magnitude squared. That gives us, expanding this out now, distributing across the parentheses, we've got u dot v minus 2 times u dot v, so u dot u, sorry, right, minus 2 times u dot v, because you've got u dotted with minus v plus negative v dotted with u. Okay, that's when we get minus 2 u dot v, plus then finally minus v dotted with minus v gives us plus v dot v. Okay, so that is the magnitude of u squared minus 2 u dot v plus the magnitude of v squared. All right, that's everybody's happy with that. Okay. Okay, so let's set these two things equal. Okay, so we have here the right-hand side of the cosine rule goes over here, and the newly found relationship we've just worked out here. Now we can see from both sides the magnitude of u and the magnitude of v, the square of each of those can be cancelled on both sides. We're left with minus 2 times magnitude of u times the magnitude of v times cosine theta is equal to minus 2 times u dot v. So let's cancel those out. And what I'm trying to do is find a relationship that relates, that help us determine the angle between the vector u and the vector v. And we can see that it's starting to show up now. So that we have magnitude of u times the magnitude of v times the cosine of theta is equal to u dot v. Okay. So by use of the cosine rule and by use of expansion of brackets, we're able to come up with an expression that helps us determine the angle between two vectors. So just move down a little bit, okay? And what that means is the magnitude of u is a scalar, it's just going to be a number, as is the magnitude of v. So we can just divide both sides by this term here, this part of the term here, and we're left with just on the left-hand side the cosine of the angle between the two vectors. I'll just go up a bit again. The cosine of the angle between these two vectors here, okay, is u dot v on the magnitude of u times the magnitude of v, okay, and this gives us the angle relationship between two vectors in irrespective, and it works in all dimensions, not just in 2 or 3 dimensions. Okay, now, so that's the angle between u and v. Let me just point something out here. Magnitude of u squared, just as a matter of interest, what does this bit up here, magnitude of u squared, means? Well, we can write that out as magnitude of u times the magnitude of u. That's just the magnitude of u squared. If we then write that out in component form, that's the square root of u1 squared plus u2 squared plus all the way up to un squared, then multiply by the same again. Okay, now if we get rid of the, multiplying these two together just removes the parentheses and leaves us with u1 squared plus u2 squared all the way up to un squared. And we can write that just as u1 dot u1 plus u2 dot u2 plus all the way up to un dot un, which just means that the magnitude of u squared, I've crammed it in here, I apologize for that, is simply the vector u dotted with itself. Okay, that's all that is. Let's have a look at some general properties of the scalar product, or the inner product, or the dot product. Okay, and the properties are simply u dot v is v dot u is commutative. The end result is a scalar in both cases, and it doesn't matter which order we dot them in, so it's commutative. Scalar multiplication, k times the product, or the scalar product u dot v is the same as k times u dotted with v is the same as u dot kv. Okay, probably in the middle there should have put the parentheses around the ku, but anyway, not to worry. U dotted with 0 is just 0, as you might expect, because it's u1, u2, u3 all the way multiplied by 0 in each case for the 0 vector. Okay, distributive law applies. U dot, the sum of v and w is the same as u dotted with v, then added to u dotted with w. A special case here, when u dot v is 0, okay, that implies that the vector u is perpendicular to the vector v, they're perpendicular to each other, or that u is 0 or v is 0. Okay, if u is 0, clearly that'll be 0, or v is 0, then that scalar product will clearly be 0. But if they're at right angles to each other, okay, if they're perpendicular to each other, we also end up with 0. And that tells you a little bit something about vector projection we'll come up to later in a future video. Okay, u dot u, as we found, is mod u squared. U dot v is mod u times mod v if and only if u is parallel to v. Okay, so u dot v, if the cosine of the angle is 1, because theta is 0, that means they are parallel. So if you've got two vectors, okay, parallel to each other, then, or however you like, but the angle between them is 0, then the cosine of 0 is 1. And so what you end up with is u dot v is equal to mod u times mod v if and only if u is parallel to v. Okay, I'll tidy up the page a bit. Whoops. There we go. Okay. All right, now, unit vector. we want, given some vector, we want a unit vector in that direction. Okay, so let's say the vector v is the vector b, sorry. Vector b is given, then a unit vector, that's a vector that has a magnitude or a length of 1. Okay, magnitude or length of 1 is a unit vector. Then we can find a vector in the direction of b that is a unit vector if we simply take vector v and multiply it by 1 over the magnitude of b, or divide it by the magnitude of b, however you want to say it. But and to denote the vector b, notice the little hat above. So a unit vector b is denoted with a little hat above it. A vector b just has the tilde underneath it, but if we want the unit version, that is a vector that has length of 1, magnitude of 1, okay, then what we need to do is take the vector divide it by the magnitude of itself, and we get a unit vector b hat. That's pronounced b hat. Okay, that's b hat. All right, that's it. Done with that.